Okay, so we've got this type of light with this particular wavelength, and I want to know what its frequency is. I want to know how much energy it produces. Okay, so what do you want to do first? We can do that one first if you want. I'd probably do the frequency one first just because it asks for it first, but I mean, it really doesn't matter. But we can do the 6.626 times 10 to the negative 34th joules times seconds. And that's great because it gave me the joule unit right where I wanted it in the numerator. Now I need to get rid of the seconds unit because I can't have that. So the only thing that I have at my disposal is the speed of light. So I'll write 3 times 10 to the 8th meters per second like this. That way I can get the second unit to cancel out. But that came with a meter unit, so now I got to get that thing to cancel out. So I do that by throwing in my 5.5 times 10 to the negative 7th meters here, and now my meters are gone. Okay, so let's see what that is. It's going to be a really small number, 6.626 e negative 34 times 3e8 divided by 5.5 e negative 7 equals, I get 3.6 times 10 to the negative 19th joules. Great. Okay, so then let's figure out frequency. So what I need is 1 divided by seconds for my answer units. So I'm going to start with 3 times 10 to the 8th meters divided by seconds. And now I have the second unit right where I want it. Now I just need to get rid of the meter unit. So I'll just use the what I was given, that 5.5 times 10 to the minus 7th meters. And now meters are gone. So 3e8 divided by 5.5 e negative 7. And I get 5 10 to the 14th. 5.5 times 10 to the 14th. 1 divided by seconds. Seconds is in the denominator. Doing this backwards kind of stopped me from being able to explain something about test taking. What's the other way you can calculate energy in these problems besides using the wavelength? You can use the frequency, right? Just Planck's constant times the frequency. If you had calculated the frequency first and then used the frequency to calculate your energy answer, that's a mistake, because you should always try to calculate an answer based off of the given information, and only calculate an answer based off of a calculation you made if you have to. So in this problem, I can calculate the energy and the frequency by using the information in the problem. And if I had done it the other way around, did the frequency first and then used the frequency multiplied by Planck's constant to get my joule answer, what'll happen is, do you see how there's a possibility of like a rounding error with that? So using calculated information will always be less good if I can use it from the problem. So the way a multiple choice exam will work is, what'll end up happening is your answer will be off by like a decimal place. So if we would have done it the other way, maybe the answer would have been 3.5 times 10 to the negative 19th. So that'll be answer A. What's answer C going to be? 3.6 times 10 to the negative 19th. So I'm saying is, when you're doing multiple choice problems, make sure that you, when you're doing standardized exams, make sure that you use given information if you can calculate the answer. I mean, that's the problem with the multiple choice exam, right? They're giving you the answer, so they have to try to fool you. All right, so I've got this frequency. I want to calculate the wavelength. I want to calculate the energy, and I want you to tell me where it is on the spectrum. So wavelength, I need length. So I'll do 3 times 10 to the 8th meters per second. So I have a meter unit, and I need to get rid of the seconds. So I'm going to actually have to put the 4.5 times 10 to the 14th in the denominator, because its seconds unit will now be in the numerator since it was in the denominator. So the seconds cancel out, and so I get 3e8 divided by 4.5 e14. So this is 6.67 times 10 to the negative 7th meters. And for my energy, I've got 6.626 times 10 to the negative 34th joules times seconds. And then I'm just going to multiply it by 4.5 times 10 to the 14th divided by seconds. Seconds cancel out. 6.626 e negative 34 times 4.5 e 14. I get 3 times 10 to the negative 19 joules. So if I look at this guy right here, I can convert this to 667 nanometers. Are we okay with me doing that in my head? If I move this thing over 1, then that becomes an 8. And if I move it over again, then that becomes a 9. And 10 to the negative 9th is nano. So I'm doing that because then I can go over to the notes and see, hey, look, right here, somewhere in here, right? That's where that would fall. And so then I can come back over here and say it's orange. Visible light, orange light specifically. All right, so let's talk about atomic line spectra. What diagram did you guys use? We can use the circle one. So I can say I've got nucleus, something like that. And I can go to a different pen here. We'll talk about, let's just do hydrogen. So hydrogen's got an electron there, and the some kind of energy comes in and hits my electron. And when that happens, then my electron jumps up to a higher energy level. And now it's hanging out up here. Doesn't want to be up there. It wants to be in what would be called its ground state, which would be as close to the nucleus as possible. So this electron bounces down. Maybe he takes 2 trips to get himself back down to where he was before. And each time he makes a trip, some kind of light is going to be given off. And this light that's being given off is its spectra. So in this case, what you would see if I was looking at like the whole rainbow, I would only get like 2 lines on it instead of the entire spectrum. And depending on the number of electrons that that substance has, and the availability of open spaces for it to jump to, it produces different colors of light. The other way we could have done this is you could have done an energy level diagram. And we could have done the same thing with an electron here, jumping up to a higher energy level and then falling back down and falling back down to where it was before, giving off some kind of light, and talking about it in that fashion. So either of those is totally fine. But when we're talking about a spectra, we're just talking about electrons on an atom that get excited, and then when they fall back down to their ground state, they lose their excitedness and release light. So what's the evidence for light being both a particle and a wave? What about a wave? What do you got for a wave?
Diffraction.
I actually don't like that word bends. I think turns is probably better because it actually takes an angle. There's no curvature to it. It's like a pool ball hitting, or like an ice hockey puck, air hockey puck hitting the wall. It doesn't curve around it. It hits it and then comes off at a distinct angle. When hitting fluids of densities. Actually, I'm getting rid of this fluids thing too. I don't like that either. Just write substances. Okay, so refraction. What else we got for it acting like a wave? Interference. It can so it can add to itself and make itself brighter, or it can cancel itself out and make itself dark. What about particle? So only single there's no interference. There's no ability to add to it. So when I'm shining blue light at a solar panel, the solar panel is activated, and when I shine red light at the solar panel, nothing happens, even if the red light is really, really big, a very powerful red light. There's plenty of energy there, but the energy comes in tiny little packets that are too small to actually do anything individually, like kindergartners.